Kia ora Year 12 and 13. This video is really for people in 13 MCA who are away from class today when I do integration by substitution, because this video goes along with a couple of applets from GeoGebra that show you geometrically what's going on. I haven't got time tonight to put those all into the one video, so I'm just going to split out these two examples, but it's really useful to get a feeling for what's happening when we actually do the substitution. Basically, integration by substitution is a way that we can change the variable from x into something else in a way that's going to make it much easier to find the integral. Now, sometimes substitution examples in textbooks can be a little bit contrived, and they're ones that you could often do by inspection. So what I've tried to do here is to pick two questions where it's not that obvious that you would do these just by looking. So let's start with the definite integral, which is this one here. So we've got the integral between 5 and 1 of x times x minus 1 to the power of a half dx. So we don't have any of our nice patterns here. This thing here is not somehow linking up so that I can easily do this backwards in my head, right? So what I'm going to do instead is I'm going to say, let's change all of the variables over. Let u equal x minus 1. Well, what we have to do is replace everything with x with a u. So this bit here is going to be fine. We need to find a way to write x in terms of u. So we're going to have u plus 1 is equal to x. So that's that bit done. Now, the dx, where does that come from? Well, we know the link between u and x. du by dx is equal to 1. We can think of this, if we go all the way back to when we started differentiating, as the change in u per change in x, when the change in x becomes really small, right? So what we're saying is basically that those two things work together. I'm going to do a classic maths teacher thing here. I'm going to hand wave a little bit. Sorry for anyone watching. And I'm going to say that that means that we can think of this as working like a fraction in the limit. Right, so here we're going to just write du is equal to dx. And we've already seen us do that thing a few times when we were doing differentiation. For example, when we were doing implicit differentiation and parametric. Okay, so this is going to be a key step whenever we're doing substitution, is we're going to find du by dx, and we're going to split it up, and somehow we're going to find a way to replace the dx. And here it's really easy. Du and dx are the same thing. Now, the last thing we have to look at are our limits of integration. These limits here are limits concerning x, right? So here we've got x on this axis, and we've got a function of x here. So we've got a wiggly line, we've got 1 here, and we've got 5 here, right? This in no way is this graph, right? It's just an example. So we're going to find that area. Now, what we're doing when we change it over is we're changing everything over to u, and that means that the 5 and 1 are going to have to change. And in this case, they're going to change so that they work out to be 0 and 4. And the wiggly line is going to change as well. And if you go to the GeoGebra applets, that's what you're going to see. And so we're going to have a different wiggly line, but the area under this curve is going to be exactly the same as the integral here. Anyway, getting back to how we change those limits over, it's not too tricky, or it's certainly not in this case. We just do a little table. Here we've got the x limits, so we've got 5 and 1, and here we've got u. So u is equal to x take away 1, so we drop each of our limits by 1. And now we're ready to replace everything, and we can say, so let's erase all of this, magically get ourselves some room. So this is now going to equal the integral between 4 and 0. Now the x gets replaced with u plus 1. This gets replaced with u to the power of 1/2. And the dx gets replaced with du. This is so much easier to work with, right? So we couldn't easily integrate this, but this is now going to equal u to the 3/2 plus u to the 1/2 du. Very easy to anti-differentiate. We're going to have u to the 5 over 2 times the reciprocal. So notice that I'm doing my usual thing where I leave a gap, up the power by 1, and then remember how do I have to adjust it. So there we go. That's what we got for that one there. So that works out to be 2/5 of, so this is the square root of 4 to the power of 5, so 2/5 of 32, plus 2/3 of the square root of 4 to the power of 3, which is 8, minus 0 plus 0. And when you clean all of that up, no one's going to want to watch this, but you end up with 272 over 15, which is about 18.1 to 3 sig fig. So that's the first one done. And in some ways I like the definite integral ones better because it's easier to visualize what's going on. So number 2, we don't have to change the limits of integration, but we have to put everything back in terms of x at the end. So here, the thing that's causing us trouble is that root x plus 9. So we'll just let u equal x plus 9. So du by dx is equal to 1, du is equal to dx. That means that we've fixed up this and this. Now we have to look at the x. Well, u is equal to x plus 9, so x is equal to u take away 9. We can change this integral now into u minus 9 over root u du. So we've gone from having a fraction that we can't work with because of this bad denominator to having a simpler fraction where we get root u minus 9u to the negative 1/2. And I really should just keep that as a u to the power of 1/2. So there we go. Right. Now what? Now we just have to integrate. Anti-differentiate. So this is going to go up by a power, so it's going to be u to the 3 over 2, 2/3, minus 9. I'm going to make this u to the power of 1/2, and I'm going to times by 2 to undo that reciprocal. If you're watching and you're feeling like you need some more practice at this, we can have a look in the old Delta book for some integration revision. Now, what does it leave me with? Well, I've got 2/3 times x plus 9 to the 3 over 2 minus 18 x plus 9 to the power of 1/2 plus c. Okay, that'll do for now. If you are good with this, then you pretty much should be good to do all of exercise 8a. I've put the questions that I want you to do into the tracker sheet, so you can have a go at those. A couple of things to notice in those exercises are that when we're finding the area under a curve, if I've got a function down here, and I'm finding this integral, then the integral will be negative, but the sign, what we call the signed area, or the area between the axis and the curve, we will treat as a positive. In other words, we're going to take the absolute value of that integral. And sometimes you can use symmetry with those questions, and you'll see a nice example of that in question 3 in 8a, and the work solutions for that are up on Google Classroom. Thanks for watching. Have a good day.